So, next chapter is going to be on alternating current circuits, and we're going to first of all talk about alternating currents, and we're going to try and find ways of describing alternating current circuits and alternating current signals, and we're going to introduce the idea of the RMS, root mean square, and then we're going to start talking about resistors in AC circuits, how they behave when they're in this AC environment. We're going to talk about inductors when they're in this AC environment. We're going to talk about capacitors when they're in this AC environment. We're going to find that they behave differently, but not. They're going to behave differently, but not unrelatedly, you know. And then we're going to try and put that together and talk about a LRC series network, a very, very, very basic tuning network, like you use to tuning a radio station. It's incredibly basic. It doesn't work very well, but it's the principle behind it. And we're going to develop language to be able to discuss that and describe it. And then we're going to just talk about, and then we talk about power in AC and the power factor. And then I think we're just about done. Oh, transformer at the end. Okay, so we end up with the transformer. So that's where we're going today. Problem. AC, so what happens is, you remember where it comes from. You have a generator that spins inside a magnetic field. You have a loop that spins inside the magnetic field. And the current goes one way, and then the current goes the other way. And the current goes one way, and the current goes the other way. So you end up with this natural cycle of the current, let me get my pen, end up with this natural cycle of the current going one way, and then it goes the other way, and then it goes one way, and then it goes the other way. That's just the design of the system. That was Tesla. And Edison was like, only use DC, and Tesla was no use AC. And the big key for AC is the transformer. The transformer is the most amazing device. Okay, so Tesla won, and we use AC. Power company makes steam using coal or gas or nuclear or whatever. Steam drives a turbine. Turbine spins a coil inside a magnetic field. We get this current out. Follows a sinusoidal relationship. Can describe it using circular motion. It's beautiful. Problem. The average current is 0 at all times. Why? It spends half the time being positive and half the time it's been negative. So if you use averages, which we're used to using for things that vary, it's useless because everything has an average current of 0. Everything has an average voltage of 0 when you use a symmetrical waveform. So we've got to find a way of dealing with that. And we need to find a way of talking about where we are in the cycle of oscillations. So let's start off with that. We're going to talk about AC sources and phasors. When a wire loop rotates inside a magnetic field, a voltage is produced. My voltage is equal to my Vmax times the sine, and the sine is of the angle, and the angle is omega t. Remember, we can describe an angle by saying, what's its omega, what's its radians per second, and how long is it? Omega, radians per second times seconds is omega, is radians. That's an angle. So I can describe where I am on this sinusoidal wave by saying, where am I on this phasor diagram, on this 360-degree or 2-pi radian diagram. And so if I look actually over here, and I've got a mistake on it almost immediately, can you believe that? I start off here, which is here, and then I come around here, and slightly before I get to the full max, I have my A. So that's where my A is. And then I get to my full max, and then I ignore that mistake. And then I get down to B, and B is here. And then I go through the 0, and now I'm in the negative voltage region, so I'm down here. and then my D is there. And so I can talk about this very nicely in terms of degrees or radians. So we talk this about being, well, this might be at, let me make something up. This might be at 3/8 pi radians. And this might be not 1 pi radians, but 0.9 pi radians. And this might be at 1.3 pi radians, and the green one might be at 1.8 pi radians, because a full cycle is 2 pi radians, yeah? If I said to you, this could be at 70 degrees, and this could be at 160 degrees, and this could be at 230 degrees, and this could be at 300 degrees, you'd feel more comfortable with it because it's in degrees rather than pi's. But you see the one-to-one relationship. Any point on this can be mapped to a point on my phasor diagram. So this is my phasor diagram, and this is my, this is my oscilloscope trace. So, boom. Okay. And because it's a simple harmonic motion, it follows a cosine or a sine relationship. And because we decided to start off over here, rather than being 90 degrees to that, we have a sine version of it rather than a cosine version of it. Yeah? Just the way we drew our diagram. Then the other thing we have to remind ourselves is that omega is equal to 2 pi times f, which equals 2 pi over the period. Yeah? It's the number of radians in a circle divided by the time taken for a circle. So I remember that one really well, and I can always figure this out. So, okay, so this is a new way of representing this oscillation. Coming out of the wall, this oscillation. It doesn't matter which wave we're in. What matters is how far we are around the wave. So it makes sense. Problem. This system has on average 0 current, so who cares? So I've got to get around that. The problem is all the negative bits cancel out all the positive bits. Well, I can solve that easy enough. I just square everything. That got rid of all the negative bits. Now I can average. My answer's too big because I squared everything. Oh, square root it. What did I do? I squared, I meaned, and I averaged, and I rooted. Yeah? So they call this the root mean square, RMS. Consider a plot of current versus time. The average value for the current in one cycle is 0. The 0 average current implies no current, but that's totally incorrect. So it's better to use the root mean square measure of current. IRMS equals, and it turns out when you do the math, it turns out that it's Imax over square root of 2, which is 70% of it, and that's what's in my head. It's 70% of the Imax value. Okay, so this value here is 70% of that value. And that's always going to be for a sinusoidal curve, and these are all going to be sinusoidal curves, whether it's voltage or current, doesn't make any difference. For a sinusoidal curve, you're going to end up with the root mean square is going to be 70% of it. So we have the IRMS is 70% of the Imax, and VRMS is 70% of the Vmax. And this is why it's important. If I have a resistor and I have an AC power supply, so here's my AC power supply, then I'm going to dissipate energy. There's going to be a power loss associated with that resistor. Power is equal to IV. Yeah? If your average current is 0 and your average voltage is 0, that's not the right answer. if you use the maximum current and you use the maximum voltage, that's not the right answer. Because it's only at the maximum voltage and the maximum current for one instant out of the entire cycle. So that's not typical at all. But if I use my root mean square, so the power is equal to I RMS times V RMS, that works. So what happens, frankly, is you get used to being able to treat circuits that are AC circuits like DC circuits as long as you use the RMS values. So you can do like a simple circuit with a whole bunch of resistors in it, you know. This is a current. This is an AC current. You know, how is this going to work? Just use RMS values and it just works out just the same. Sometimes you forget and you don't realize you're using RMS values because all the questions are given in RMS values. But sometimes they'll give you a maximum value just to see if you're going to use it. You know, will you use that maximum value? So don't fall into that trap. Whenever you're around AC, ask yourself, am I in RMS or am I dealing with RMAX? RMS, or am I dealing with the maximum value? So I RMS, V RMS, or I max, or V max. So an AC current has an amplitude of 10 amps. Amplitude is the maximum current. What is the RMS? IRMS equals 70%, 0.70 of I max, which equals 0.70 of 10, which equals 7 amps. An AC EMF has an amplitude of 15, so V RMS is equal to 0.70 times V max, which equals 0.70 times 15, which equals going to be 10.5 volts. I think I'm right on that. 10.5 volts. 70 plus 35, 10.5, yeah. Cool. Okay. I'm going to set up, we've got 5 minutes, so I'm just going to set up this next little bit. In the next 3 slides, we're going to look at, am I right? Is that right?
6:38.
Oh, I got plenty of time, isn't it? We're going to continue then. Yeah, good. Yeah, sorry. So in the next 3 slides, we're going to deal with the way that the current and the voltage behave when AC is applied to a resistor, when AC is applied to an inductor, when AC is applied to a capacitor. We're going to see what we can learn about the patterns of behavior. And then we're going to use that knowledge to be able to, we're going to use that to invent a term called reactance, which is like AC resistance. And then we're going to use the reactance to develop a thing called inductance. No, I'm sorry. Impedance, which is like AC resistance. And then we're going to do some analysis with it. I want you in this section, this is my tip. If you look in the book, well, these are LRC circuits. Now, if you look in the book, I don't think they're called LRC circuits. Anybody got their book on them? Doesn't matter. They're not usually called LRC circuits. They're usually called RLC or RCL circuits. And I much prefer to call them LRC circuits because what we're going to find is that when we look at our phasor diagrams for these things, yeah, RLC. The book calls it RLC. When we look at our phasor diagrams for these systems, the L leads, the R is second, and the C is last. So this is my like cheating business, my self-prompting. If they're going to be LRC, why not call the circuits LRC and then I know the order, rather than calling them RLC and then not knowing the order? I mean, there's no logic behind this, in my opinion, but there is logic behind that. So don't get confused. Don't think it's a different type of circuit. It's just, when I was trying to drive into my head the order for these phasor diagrams, I just looked back and said, why do we call them by this other name? Okay, so let's begin. We have an AC source, and the AC source is a sinusoidal source, so it's going to be a maximum value modified by the sine of a time-dependent angle. Okay, that's what's going on here. And then we have our resistance and our potential difference across our resistor, and our current flowing through our resistor is what we want to look at. And if we use Kirchhoff's rules, we say, well, within a loop, then the net voltage is 0, so my delta V, my potential, my EMF at any time, summed with my potential difference across my resistor, it's a negative sign because it's the opposite sense, equals 0. So then I can say, well, hold on, I know what this voltage is at any time. And I know by rearranging that this equals the voltage, so delta VR, the voltage across my resistor, is equal to delta V max sine omega t. And I know from simple Ohm's law that I equals V over R. So I use little I for AC. Again, little I is used in math to mean what? Square root of -1 or something? It's not the same I. So don't get confused about that. So little IR, the current through the resistor, is equal to delta V max sine omega t over R. Well, delta V max over R is I max. So my current any time through my resistor is equal to the maximum current times the sine of omega t. It kind of works nicely, and it seems a bit trivial. And when I plot it out on a phasor diagram, so this is like an oscilloscope. Well, it's not like an oscilloscope. This is like an oscilloscope. This is time, and one trace can be my current flowing through this circuit, and the red trace will be the voltage drop measured across here. So I can have my V measured there, and I have my I measured there, and I'm plotting those two guys out. And what I see is when there's no voltage, there's no current. When there's a maximum voltage, there's a maximum current. When there's no voltage, no current. When there's a maximum negative voltage, there's a maximum negative current. That's kind of what you expect, really. And here's the interesting plot, which is when I plot out on a phasor diagram, so I'm going to basically pick an instant in time, then, and I send this across here, I get two different traces. Now, I can see from this, they're both at the same phase angle, and they have different lengths. If I had chosen that point there, I would have been vertically upwards. If I chose, I'm sorry, this point over here is there, that point is there, this point would have been over here. If I'd chosen that point down there, I would have been down here. If I'd chosen that point down there, I would have been down there. That's a phasor diagram. The key thing here is that the two of these things, my delta V and my I, are pointing in the same direction. They have the same phase. When one's a maximum, the other's a maximum. That's the key thing. Okay? Let's replace the resistor with an inductor. Well, I start off the same way. Kirchhoff's loop rule says my little bit of voltage is equal to the voltage across the inductor. My EMF voltage plus my voltage across the inductor must sum to 0. And I know that in this case, whereas before, look for the similarities between these pages. Whereas before, I said that my just bear with me 1 second. Yes. Whereas before I said my delta V is equal to delta V max sine omega t, yeah? I did that, yes? Here, oopsie daisy, I'm going to say, well, my delta VL is equal to L di by dt. Yeah? So, remembering that delta V is equal to delta V max sine omega t, and substituting in for L di by dt, I don't know how many steps to show on this, so delta V max sine omega t di equals delta V max over L sine omega t dt, and if I integrate that, I get I is equal to delta V max over L times the integral of sine omega t dt. So I, through my inductor, is equal to minus delta V max over omega L, because I take that out, cosine omega t. And then what I do is I compare, I compare my current having a cosine term with my voltage having a sine term. So what this says, and so what I can say is, oh yeah, my cosine is equal to minus sine omega t minus pi over 2. That's a trig function that you did years ago, but just look it up if you don't remember it. So when I substitute that in for that to get a sine again, I see that rather than it being sine omega t, it's sine omega t minus pi over 2. Now, let's be clear. If you'd left it as omega t and worked out an answer, it would be the correct answer. It's not one of these things where we're changing the answer. We're just expressing it in a form which allows for contrast. So we're using this obscure piece of trig to enable us to go from a sine to a cosine. And then we're basically saying, okay, well, actually it's not that obscure when I think about it. But then what I say is, okay, so we do that. So now we see the angular difference. And the angular difference appears on here. So if my voltage is at omega t, my current is at omega t minus pi by 2. And pi by 2 is 90 degrees. So this is 90 degrees behind. Okay? So mathematically we justified what we observe on the oscilloscope. And you do observe this on the oscilloscope. I can show you it. Not tonight. Well, I should have brought it in actually. I can show you that. You can actually see that it's 90 degrees behind. Okay? It's a real event. Okay. And this to do with, you get your, it's this di by dt business in the basic equation. So you get, when this is the steepest slope, you get the biggest effect. When this is basically no slope, you get no effect. So it's not about the maximum. The IV is all about the maximum current, maximum voltage. This is about the rate of change of. And so there's this 90 degrees phase difference. You can conceptually talk about it, you can mathematically prove it, but it's there. Now, if I think about I max is equal to delta V max over omega L, where does that come from? I max equals my, so where does that come from? I max is equal to delta V max, my maximum voltage, over the angular frequency times my inductance, which equals, Where does that come from? It comes from there. It comes from there. So I max is equal to delta V max over omega. Well, when does that happen? When that equals 1, yeah? And if I think back about I max for a resistor equals delta V, and if I remember that I is equal to V over R, this is behaving a bit like a resistance. So let's call it a reactance. It's called an inductive reactance. And what do you think its units are in? It's behaving like a resistor. Ohms. So the inductive reactance is the inductor's equivalent to resistance. It is, if you think about it, if XL is omega L, if I double the size of my inductor, I get twice as much inductive reactance. If I double my frequency, I get twice as much inductive reactance. So in a graph of XL versus frequency, let's say omega, we get a straight line. Okay? That you need to know. I need you to be able to calculate what my inductive reactance is for a given inductor at a given frequency. I need you to be able to calculate that. So write that in fire on your page. Okay. But do the same analysis on a capacitor now. Voltage equals charge over the capacitance, and my voltage is this sine function, and I can go through and yada yada yada, and I end up with a cosine as opposed to a sine, and I end up with this situation where when I make it all sine, so I can compare that guy there with this guy here, it's omega t plus pi over 2. So again, it's 90 degrees phase shift, but now it's phase shifted the other way. So whereas before my current was lagging, now my current is leading. And again, I can say, well, hold on, my I max is equal to omega c delta V max. Omega c delta V max. And so this looks a bit like an inductance. This looks a bit like a resistance term. And so I say, well, I can define my capacitive reactance as 1 over omega c. So this is my XC, and this is omega, and this is an inverse relationship. Again, I need you to be able to calculate what the capacitive reactance is at a given frequency for a given capacitor. Let's just call this stuff resistance. Let's call this frequency. If my inductive reactance goes like that, and my capacitive reactance goes like that, and I have a circuit that contains both a inductor and a capacitor, then my total resistance is going to be the sum of these two. And what happens is these guys kill you, and it's got a minimum there, and it goes back up again. So the sum looks like that. And there's a sweet spot where you have the lowest resistance associated with these components. And that is the tuning frequency for your circuit. That's when you turn the knob on a radio set, that's what you're playing with. You're playing with where this minimum resistance point is. And you're doing it by changing your inductance or changing your capacitance. Usually it's changing your capacitance, but you can do either one. That's where we're going. We're not there yet, but that's where we're going. What's the reactance of a 5 Henry inductor when 5 radians per second AC is applied to it? So my reactance of my inductor, my XL, is equal to, what was that? That was the linear one, wasn't it? Omega L, which equals omega, which is 5, times L, which is 5. Ooh, shame on me. 25 ohms. Now, what can I do to make it a bit more interesting? I could give you the frequency in hertz and have you see if you're going to convert it for me. That's one thing I could do. I could give you not henries but micro henries. This is a great time to, put your prefixes in. What is the reactance of a 10 farad capacitor? XC is equal to, that was the 1 over, wasn't it? 1 over omega C, which equals 1 over the omega. Oh, and wouldn't you know, I didn't even remember I'd done this. Man. I think it's 54. I'm going to say it's 54 anyway. So this is going to be omega equals 2 pi times F, which equals 2 pi times 54. Omega is equal to 108 pi, which equals 108 times pi, which equals 339. Did I do that right? Yeah. Radians. Did I do that right? Omega 2 pi. Yep. So this is 339 times radians per second. 339 times 10, which equals 1 divided by 3390. And I'm going to get that. Okay. And then what is the resistance of a 10 ohm resistor at that? That's, if anything, the trick thing. R equals R. There's no frequency dependent effect on it, which equals 10 ohms. So have that skill. It's not a difficult skill. Just know it's important. So have that skill. Next, let's put these in a circuit. And let's be smart. Let's put the L first and the R second and the C third. Why not just set it up the way we're going to think about it? And the trick is, series circuits. What is common to all those components? Is it potential difference across them or the current flow through them? So what I want to do, whereas in these previous examples we kept the voltage in the same place and we looked at how the current moved, now we want to keep the current in the same place and look at what's going on with the voltage. Actually, what I'm going to do is look at what's going on with the resistance, with the reactances. But the linking is, the current's the same through all of them. Okay. So we say, consider a series network consisting of a resistor, an inductor, and a capacitor. The current in all parts of the series AC circuit has the same amplitude and phase. The instantaneous voltages are out of phase with each other. So the EMF here at any instant, the EMF here at any instant is not the arithmetic sum of the potential differences. It's the vector sum of the potential differences. And that's weird. Because it turns out that when this voltage is pointing upwards, that one is pointing downwards, and so they are opposing each other. And that's just, that's why you have phases in. They're not there just because we like them. We're there because we've got to deal with a vectorial sum of these potential differences. Okay. So I can't just add these numbers together. I've got to think about them in terms of a diagram. Well, this is not a very good diagram. It's the right diagram. It's a correct diagram, but man, it doesn't tell me anything. You know. So here's the voltage across the resistor, and then the voltage across the inductor is a little bit ahead of it, and the voltage across the capacitor is a little bit behind it. You know. At that point there, I'm confused. You know, it's kind of like this one's negative, that one's positive, this one's positive. You know, this is not the way to go. It's the way to visualize, but it's not the way to go. So how are we going to figure this out? We're going to say that our voltage across the resistor equals I max times R. My voltage across the inductor is I max times XL. My voltage across the capacitor is I max times XC. V equals IR. It's just expressed in AC terms. Okay. Well, I know my voltage is I max R sine omega t, which equals delta VR sine omega t. And I know my delta VL, the voltage across the inductor, equals I max XL, rather than R we have XL, sine omega t plus pi over 2, because that's what we learned the phase difference was. And then for the AC, for the capacitance, it's I max times not XL but XC, sine omega t minus pi over 2, which gives me that. So yeah, I can look at this and I can figure stuff out if I know my omega, etc., etc. But this is a better way. You draw it out and you say, well, if that's the voltage across my resistor, and that's the voltage on my inductor, and that's the voltage on my capacitor, these two are just vectorially fighting each other. So I add them up and I get that as my resultant, and then, oh, that's my maximum voltage. Just using Pythagoras. It's like, it's beautiful. And what makes it actually even better, I think, is if you do it this way. Plot a phasor of resistance. Okay. So you have your XL, you have your XR, and you have your R. And when XL is bigger than XR, your overall resistance, which is a Z, it's called Z, which is impedance, is in a positive angle direction. And if you, and what causes this? What causes this is the relative size of XL versus the relative size of XR. Now let's remind ourselves of that graph. We had R, we had XL, and we had XC. So if I have a low frequency, then my XC is bigger than my XL. And if I have a high frequency, my XL is bigger than my XC. So I can dial in what I want by which frequency I choose. If rather than having a high frequency, this is high frequency. If I have a low frequency, then what's going to happen is I'm going to get a big, sorry, this is XC at the bottom. I have a big XC. I have a small XL. I have the same old R. And so There's my Z. And my phase angle is in a negative direction. Looking at this, if I add these together, the minimum value for the sum of these resistances is at this sweet spot. It's called the resonance frequency. The minimum value occurs when my XL is exactly equal to my XC. And then my Z is simply equal to my R value. My impedance is equal to my resistance. That's your tuning frequency. That's when everything's lined up perfectly. So the skills I need to be able to evaluate XL at a given frequency for a given inductor. I need to be able to evaluate XC at a given frequency for a given capacitor. I need to know this diagram so I can combine them and figure out what my Z value is. And mathematically, my Z value is equal to the square root of the horizontal bit, which is R squared, plus the vertical bit, which is XL minus XC all squared. That is telling me this diagram. That's basically, I don't remember this equation. I know the diagram. And once I know my Z, then my V max is going to equal I max times my Z, because Z is just like a resistor. And this angle, this phi angle, well, it's just going to be the opposite over the tangent of the opposite over the adjacent, which is XL minus XC over R. So those three, really important. So we had, that's important, XC is important, XL is important, and those three are really important. And the way you solve these is you say, oh, what was the frequency? Oh, I'll work out what my XL is. Oh, what was the frequency? I'll work out what my XC is. Oh, what's my Z? What's my impedance? Oh, I'll work out what my current is. Boom, boom, boom. It's like that. It's a bit of a set piece. And what happens is, I'm going to jump a slide because I'm almost running out of time, but what happens is that because as the impedance gets less to its minimum value, then your current gets bigger. So here's a typical frequency versus current plot. And when you have at whatever frequency you have for your sweet spot, you get the maximum current. Now, what can you tell me about XL and XC at this frequency? They're the same. So at that frequency, they're the same. And I'd like to know what that frequency is. Well, if XL equals XC, then omega L for this frequency is equal to 1 over omega C for this frequency. So omega is equal to the 1 over the square root of LC. That tells you that frequency. So for a given LRC system, I know the sweet spot frequency. It's called the resonant frequency. I know the resonant frequency. And I know that at that resonant frequency, my resistance, my impedance of the circuit is equal to the resistance, because the XL cancels out the XC. That's one set of questions. And then what I can do is I can take you off resonance. And I can say, well, at this other frequency, what is your XL? What is your XC? What is your Z? What is your phase angle? Boom, 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 boom. So let's try and put this in perspective. Oh, so what am I showing here? I'm showing here the effect of different resistors. Clearly, if I have a small resistor, I have more current. If I have a big resistor, I have less current. So the peak is sharper for the smaller resistance. So ideally, I'd like I like an L, I'd like a C that cancel each other. I like an XL and an XC that cancel each other, but I want an R as small as possible. And I can't always get the R as small as I'd like it to be. This shape is important because what's going on here? I have a radio station at one frequency. I have a radio station at another frequency. And I have a radio station at a third frequency. And my antenna picks up all three of them. The antenna just measures what it gets. It gets every frequency of every radio station in the vicinity. So why don't I hear those three stations? Because at this frequency, my current is next to nothing because my impedance is so high. And at this frequency, the current of my signal is next to nothing because the impedance is so high. And at this station, at this frequency, my current is as big as I'm going to get because the impedance is the minimum value. So I hear this radio station rather than these two because its signal causes the biggest current with the way I've got my circuit tuned. And if I have a cheapo radio, then I get nice broad curves and I hear a little bit of the other radio stations. If I have a nice expensive radio, man, I don't hear anything from those other guys. And what's the difference? They don't use this circuit. They use a tank circuit. They use a better circuit. It's more hard to analyze. It's harder to analyze. But this in principle works. And this is money. You know, if the government could do, they'd make it so the radio stations were infinitely close together and would have an infinite number of radio stations. And they would rent out that frequency spectrum. And if you could get 10 times as more radio stations and still only hear one radio station, you'd have 10 times the revenue for the government. So this makes a lot of sense. They want things to be as discriminating as possible, but there's certain limits on what they can do. This is kind of where we're going. There's a thing called the power factor. Engineers like to talk about quality factors. A quality factor. And the quality factor is basically, it is the resonant frequency divided by the full width at half max. So you go to your resonant frequency and you plot this out and you say, how wide is this? And it's, you know, this would be 10 divided by, 10 divided by, that's about 0.6. Let's call it 0.5 and I can do the math. That would be 20. That's my quality factor. It turns out that that's going to equal omega naught L over R. And so if I can make a circuit with a big L and a little r, I have a very nice quality factor. Okay. Yeah. So what's the skill set? The skill set is, I'm trying to find a relatively blank page. What's the skill set? The skill set is, can you do RMS? And then can you do XL and XC? And then can you do the phasor diagram and find me Z and find me the phase angle for a given frequency at a given omega? And can you find the resonant frequency, the omega naught. And can you find me the quality factor? So that's so far. There's a little bit more to come in the next little bit. But I'm going to, oh, have I got time? No, I've not got time. So those are the bits on this. And this is going to come up. I can tell you now. I'm going to give you an LRC circuit. I'm going to say, hey, what's the resonant frequency of this? I'm going to say, oh, by the way, at this other frequency, what would be your capacitive reactance? What would be your inductive reactance? What would be your impedance? And then, oh, by the way, what's the quality factor? If I give you these other numbers, what's the quality factor? So this is, I can't get through this bit and not ask you about a tuning circuit. So it's money in the bank. Okay? Questions? Let's end it there then.